Hi, myself Milan, and my other teammates are Suraj, Vinith, and Vignesh. As a part of RB51, I mean Robot Dynamics course project, we did kinematic and dynamic analysis of the Baxter Robot for pick and place application. So in this video, we will be explaining you about the different portions of our project. So let's get started. So before I start introducing you to the Baxter Robot, so this will be the layout of this video. I will be introducing you to the Baxter Robot, as well as I will explain pH parameters, workspace, and forward kinematics of the Baxter. After me, Suraj will explain about inverse kinematics, and after that, Vignesh will explain about velocity kinematics as well as dynamics of the Baxter, and at last, Vinith will explain about the simulation and the future scope of the project. So as you can see here, Baxter has two arms, and it quite resembles with human because it has torso and head, as well as both of arm has 7 degrees of freedom. So that's the reason it has many applications in variety of areas. For example, in the industries, it can be used for pick and place application, as well as for sorting in or for packaging. The next area is academic and research. As it has two arms as well as high degrees of freedom, many researchers are currently working on as a part of a maneuverability project. And then in case of medical and healthcare field, Baxter is also very useful because of high degrees of freedom. For example, it can be used as a nursing robot, and at last it can be used for testing as well as quality inspection. So these are the coordinate frames of the Baxter. As you can see, in the left arm there are total 7 joints. The same joints are there in the right arm, and all of the joints are rotary joints. The first joint is S0, which stands for shoulder 1, same way S1 shoulder 1, E0 elbow 0, E1 elbow 1, W0 wrist 1, W0 wrist 0, W1 wrist 1, W2 wrist 2, and at last there is a gripper. So depending upon the version, it may have or it may not have the gripper, and these are the coordinates frame at each of the joint. I will explain you later, just after a couple of slides about this. Yeah, so these are the pH parameters of the Baxter, and both of the arm will be having the same pH parameters because they have the same configuration. And this is the workspace of the Baxter Robot. The orange area is the workspace of its right arm, while the another one is for its left arm. So now forward kinematics. So what is forward kinematics? So in forward kinematics, we will be knowing about the link length as well as all the joint angles, and with the help of these parameters, we need to calculate the position as well as orientation of the end effector. So how we will do it? So the most easiest and widely used method is homogeneous transformation matrix. So what is that? So let's get back to some slides. So as you can see here, in this method, at each joint we will assign a coordinate system. So this is x0, y0, 0. Same way till we will assign this coordinate system till end effector. So, and for each joint pair, let's say for S0, S1, S1 E0, E0 E1, same way till W1, W2, we will calculate one homogeneous transformation matrix. So what it will do, with the help of those transformation matrix, we can relate this frame with this frame, that will be A1. With A2 we can relate frame at S1 with frame at E0. So to relate base frame with the end effector, we will multiply all of this transformation matrix, and we will get the relation between end effector and the base frame. And in case of Baxter, we will assign coordinate system at its we will assign coordinate system at both of his arm, and there will be one extra common base frame which will be located at the center of its torso, so it will be easier for the calculation. So now my friend Suraj will explain you about the inverse kinematics. Thank you.
Thank you, Milan. Alright, now we will start with the inverse kinematics. So in the inverse kinematics, we have the position in the world coordinate frame, and our task is to find the corresponding joint variables. Inverse kinematics is difficult for the serial manipulator because there can be many configurations for one position and orientation. Also, there is no universal way to solve this problem. However, this problem can be approached with different ways. Specifically for Baxter, we can use two approaches to solve this problem. In first approach, we convert the robot into 6 DOF configuration with spherical wrist. Then we can break the problem into two sub-problems, namely inverse position problem and inverse orientation problem. We can solve the inverse position problem using geometrical method, and for inverse orientation problem we can use the Euler angles. Computational overheads in these methods are less. However, it is not possible to convert every robot into 6 degree of freedom robot with spherical wrist. Also, converting the robot into 6 DOF configuration, we lose 1 degree of freedom. In our approach, we use Jacobian-based iterative optimization method to solve this problem. This method is universal and can be applied to any serial manipulator. However, the method is trade-off between computational cost and accuracy. In our method, we first calculate the error. Based on the error and the Jacobian at that position, we decide how much each joints need to be moved to get to the final position. After reaching the next position, we will calculate the forward kinematics, Jacobian and error at that position, and if the error is above the threshold, we will repeat the above steps until the error converges to the threshold value. You can see the result of this method in the following slide. In the first graph, which is the graph of number of iteration versus error, you can see how the error is converging. You can see the result of this method in the following slide. The first graph is the graph of iteration against the error. As you can see in the graph, the error is continuously decreasing over the number of iterations. The second graph is the position of the robot versus the number of iterations. As you can see, the robot is achieving the final position based on the numerical on the iterative solving method. For the faster execution, we are planning to couple this method with following approach. In this approach, we will divide our workspace into bins, and for each bins we will store the corresponding joint angle. Whenever we will receive the position, we will try to find the bins corresponding to that position. Based on the bins, we will retrieve the joint angles, and we will give the same to the robot controller. In the meantime, we will start calculating the inverse kinematics from the bin position to the desired position by iterative method. Once robot reaches the bin's position, we would have already calculated the inverse kinematics for the robot, and this will save the time and computational overhead. Now Vignesh will explain you about the velocity kinematics and dynamics for the Baxter robot.
I'll be talking about velocity kinematics of Baxter now. So basically, velocity is the change of joint variable with respect to time. So for a robot, usually we find the velocity and effector velocity by multiplying the Jacobian and the each joint velocities. So Jacobian matrix is basically a matrix which has values which has rate of change of end effector with respect to the joint variable. So usually it is found by taking the final homogeneous matrix, the position vector, and differentiating it with respect to the joint variables. It has two components, linear and angular velocity components. For a prismatic joint, the angular components are considered 0, and uh, sometimes you can even when you need to, you can calculate the inverse velocity kinematics, which is basically using end effector velocity and Jacobian inverse to calculate each joint velocities. And since Baxter Robot is 7DOF robot, it has lot of redundant joints. So there are many ways in which many joint variable combinations which can finally result in the same end effector velocity. So that can be used as an advantage also in certain situations.
The dynamics of the Baxter robot. Basically, dynamics is finding the relationship between forces and the resulting acceleration we get from it. So usually two approaches are followed to find the dynamics of a system. One is Euler-Lagrange approach and the other is Newton-Euler approach. So we have followed the Euler-Lagrange approach for our finding the dynamics of Baxter robot. As you can see, the formula is torque is equal to inertia matrix into the joint acceleration plus the Coriolis force term into the joint velocity plus the gravity vector. And now we have wrote the code in MATLAB to find the torque equation for Baxter's robotic arms. The code looks as shown. So first we have initiated all the variables which is required, and few of the terms have been used as symbolic representation so that we can use it in the code. First, the center of mass of each joint is found out. These values we got from the Baxter's Rethink Robotics site. Then we have calculated the DH parameters for each length and used it to find the homogeneous transformation matrices. And the homogeneous transformation matrices have been found with respect to the base frame, and it is done for the left arm and the right arm. And now basically we use the formula that Lagrange equation is equal to kinetic energy minus potential energy. So we are first finding the potential energy. The potential energy term is basically mg and the position. So the position is found by the z vector in the fourth column of the homogeneous transformation matrix. Similarly, it is found for all the 7 links and for left hand and the right hand. Finally, we add the potential energy terms for all the 7 links. Then we go into the kinetic energy term. The kinetic energy term has the velocity terms in it, and now velocity is found by taking the fourth column in all the final homogeneous transformation matrices of each link and differentiating with respect to time. And similarly it is found for the right arm also. And then we do use the formula kinetic energy is equal to half mv square. As you can see, finally we add all the kinetic energy for all the 7 links and we get the total kinetic energy for left arm and right arm. Now we use the formula Lagrange value is equal to kinetic energy minus potential energy. So next we need to find the torque of each arm. So torque is equal to, we know that it's equal to d by dt of dl by dq dot minus dl by dq. So we use functional derivative in function in MATLAB. It helps us differentiate the Lagrange value with respect to each of those theta values. And then we are finding the terms for kinetic energy in left and right arm so that we can find the final Lagrange equation. And as you can see, we have found the torque for each arm, which can be used to find the joint velocities. It is quite big because of the 7DOF, since it's a 7DOF robot and the large number of variables present. And basically this is what we have done for the dynamics part of the project. Thank you.
So let us move on to the next set of our presentation, which is a gazebo simulation of our Baxter robot. So what is gazebo? Gazebo is a physics engine. It contains a physics engine which has real world effects embedded in it. And why we use gazebo? Gazebo has
a lot of support packages that are provided many third parties also by Rethink Robotics exclusively. And also it has flexibility to run with ROS and MATLAB. There are similar other simulators that can be used with MATLAB like VREP, but we are using Gazebo in our for performing our Baxter simulation pick and place. The system setup that we used was Ubuntu 14.04 and ROS Indigo environment, and we are using RSDK, Rethink Software Development Kit, the packages in it. Let us see the pick and place demo first. So as you can see, only the left arm is active, so we are trying to use only the left arm throughout our simulation. So before even we launch our Gazebo simulator, we need to configure the IP address and local host name of the Baxter Robot that we are trying to use, all of which can be changed and configured in the baxter.sh file. So this is a Baxter simulator, and you can see this is a Gazebo environment. So it has loaded all the world files that we require and the 3D model of the Baxter Robot. Once we have all this set up, we can run our pick and place demo. Now you can see there's a table and a solid object at a particular defined position that has been included in the Gazebo 3D environment. Now you can see the left arm performing the picking operation goes into the pertinent orientation, the set orientation of the solid block, computes the inverse kinematics, estimates the angle, gives us the takes the joint angles and then feeds into the individual joints. So the gripper holds onto the object. Once it holds onto the object, it hovers over to a certain distance, places the object at a given set point. So the whole model of this pick and place is not a closed loop system, hence there is scope for performance improvement. There is no feedback mechanism, to be precise, so we can give the feedback using a vision based information or like visual based surveying systems. So that's it about the simulation part. Coming to the code, you can see there are a lot of modules that have been included. There are some ROS modules that have been included, and there are Gazebo libraries. The messages are for communication between the ROS and Gazebo, and there's a Baxter interface that contains all the necessary modules, the core modules for the controlling the Baxter robot. And as you can see, there's a pick and place method. This is a class in which there are many sub methods. I'll only be discussing about the main sub methods that we are using, which is move to start. So this guides the joints to move to a starting position by specifying the joint angles, and given IK request, given a pose or that's the state of the particular position, it computes the angles, and the gripper open, gripper close are some of the almost necessary methods. So this is a pick method that is defined in this way, and then the place method, and then you can see the main function has like loads on the Gazebo models, and we define the hover distance, and starting joint angles are defined, and then we call the pick and place object, and that's pretty much about the code. Let us move on to the future scope of the project. So as you can see, this is only the 3D simulation which is performed on a virtual Baxter robot, and we didn't yet implement this on a real life Baxter robot. So the next target would be achieving the same on a real life Baxter robot. Also, we can use vision based we can move on to developing a vision based pick and place application instead of just a Cartesian based approach that we are doing right now. Also, the existing Jacobian based numerical method is computationally very intensive, so it takes more time to give us the results that we require. Hence, we can move on to a cyclic coordinate descent based algorithm to compute the inverse kinematics. Thank you.